Hello class, and welcome to the fourth lecture on concrete and the second lecture on properties of hardened concrete. In this lecture we're going to talk about shrinkage, a term that we talked a little bit about when we discussed cement, because the type of cement you use influences shrinkage. And also we're going to be talking about the durability of the concrete, some of the things that can happen to the concrete throughout its lifetime that can decay the concrete and make it ineffectual for whatever civil engineering infrastructure it's trying to perform as a component. So let's get underway and immediately talk about shrinkage. Well, shrinkage is basically where the concrete gets smaller. It loses its volume, and this happens in the first few weeks of the concrete's life while it is undergoing hydration and the cement is reacting with the water. Now, shrinkage occurs in three dimensions. So if you have a concrete block, it's going to shrink in its length, its width, and its depth, its height. It's going to shrink in all three dimensions. Now, there's two things which lead to this shrinkage. The first one is quite easy to understand. That's drying shrinkage. Remember that only about 350 mils of water for every kilogram of cement in the concrete will be used in the hydration reaction. All the other water, the excess water, that's just in the concrete so that it has good workability and so it has a high slump. Now that excess water is going to evaporate from the hardened concrete. Now when that happens, the concrete is going to first have voids inside it, so that's why a high water content leads to a weaker concrete, but also it's going to shrink ever so slightly, and it's a tiny amount. It's about 0.1% in each dimension, height, width, and length. The other cause of shrinkage is a little bit harder to understand, but this is called plastic shrinkage. Now this is where the hydration reaction results in a net reduction in volume. So remember what we talked about, where basically you will have a cement molecule, be what it be, dicalcium silicate, tricalcium silicate, or tricalcium aluminate. Now that has a volume to it, that molecule. When it becomes hydrated with a water molecule, or several water molecules in fact, those water molecules, they have a volume to them too. Hydrogen dihydrogen oxide is H2O. That's what water is. Now, I don't know if you remember from chemistry, but the shape of a water molecule is actually like Mickey Mouse. You've got an oxygen atom, and it's got two hydrogen atoms holding to it like two Mickey Mouse ears. Now, when they react with cement, they basically interlock with the cement molecule, and the net volume of the product is smaller than the sum of the volumes of the reactants. So if you have a dicalcium silicate, and that's reacting with 8 water molecules, the overall volume there of the reactants, the 8 water molecules and the dicalcium silicate, that will be more than the product, which is basically a hydrated calcium silicate. So that leads to an overall reaction in the volume of the concrete. And again, it's very, very small. It's about 0.1% in height, length, and width. Now that 0.2%, the sum of the plastic shrinkage and the drying shrinkage, that may not seem like a lot. However, if you're building a very large concrete structure, and as civil engineers we often are, that will lead the concrete to crack. And so that's a big problem. We don't want concrete cracking when it's brand new. So these are shrinkage cracks. You can see here that someone has built a very long concrete driveway, and cracks have emerged in the concrete. Now notice how those cracks in the concrete are perpendicular to the longest length. They go across the road. Well, think about it. If the shrinkage is a percentage of the dimension, well, the amount of shrinkage in terms of millimeters will be much more on the long length of the road than it will be in the short width of the road or the thin thickness of the road. If it's 100 meters in length, it's going to shrink, if the shrinkage is 0.2%, it's going to shrink up to 20 centimeters if it's 100 meters in length. So that's going to mean you're going to have a lot of perpendicular cracks along the road. But if it's only, let's say, 100 millimeters in thickness, well, the shrinkage in the thickness of the concrete, well, that's only going to be 0.2 of a millimeter. So that's tiny. That's not going to crack. And if it's only 5 meters across, well, that's going to be, what's that going to be? That's going to be, that's only going to be about 1 centimeter. So there might be some cracking that occurs in the width of the road, but most of the cracking will be perpendicular to the longest length, because that's where most shrinkage is occurring. And you can see shrinkage cracks at various places. I challenge you to visit when we get back to the university, look at the concrete driveway after you come through the entrance where the Vice Chancellor parks his car, and other places. You will see that there's actually certain shrinkage cracks in the concrete there. Also, there's shrinkage cracks around the concrete work surrounding Family Mall and also Park View. Those are examples. You're going to be so interesting to your family by the time you finish this module. You're going to be looking at concrete, and every time you see a crack, you're going to be able to tell your family how that crack came to be. It's going to be very exciting. So, what do we do to minimize shrinkage? Well, potentially it doesn't matter if the concrete cracks. For certain things like footpaths and things, it doesn't matter too much. But it can be a real big problem with things which need to be watertight and also very strong. So a dam, for example, you can't have cracks forming in that concrete wall. If that happens, the dam's going to fail. Likewise, if you have shrinkage cracks in a building column, that's a big problem because cracks reduce the strength of the concrete. Well, one of the good ways to minimize shrinkage is don't have excess water. Make sure you don't have too much water. And that's going to reduce the drying shrinkage. It won't reduce the plastic shrinkage, but it will reduce the drying shrinkage, which is often about half the amount of shrinkage. Now, the trouble with that is if you don't have more water, you're going to be reducing the slump. You're going to make the concrete less workable. And so it's all about having a balancing act. One thing you could do is have water-reducing admixtures, things which dehydrate the concrete. Again, that will reduce the workability of the concrete. But one thing you could do is use something like a plasticizer. Now, a plasticizer is basically a chemical that you can add to your concrete mix, which gives it more workability. It increases the slump without having to increase the amount of water. You're going to learn more about admixtures when we do concrete technology. There will be no questions about admixtures in the building materials assessment. Another way you can reduce shrinkage is to be careful about what kind of cement you use. Non-hydraulic cements, things like lime, or hydraulic, non-hydraulic blends, something like Portland cement pozzolan. They have less shrinkage. They have a lot less drying shrinkage, but particularly less plastic shrinkage. And that is the key reason why the dam at Mosul was made out of Portland pozzolan cement in the concrete. They imported pozzolan from New Zealand and they mixed that with Portland cement, which they had made in Sham Shamal. Now, those certain kinds of cement, they have less shrinkage because the volume of the product in those hydraulic reactions, those hydration reactions between the cement and water, the volume of the product is very similar to the volume of the reactants, and so there's very minimal shrinkage. With Portland cement, just plain type 1 Portland cement, there's going to be more shrinkage because the product is smaller than the sum of the reactants. Now, there's another way you can manage shrinkage. What we talked about in the last slide was ways of minimizing shrinkage. And that's important, particularly if you can't manage the shrinkage. Those issues of having less water, well, that reduces the workability of the concrete. That may not be practical. Using plasticizer or an admixture, that can be expensive. Or using a blend such as Portland pozzolan cement, well, that's going to be very expensive because pozzolan's expensive. You have to import it from a volcanic country like Iceland or New Zealand, which are far away. Or the other option is you could use something that is non-hydraulic like lime, but you're going to lose a lot of strength in your concrete. But there are cases where it's okay to have gaps in the concrete, and I'm thinking examples such as concrete roads or concrete footpaths. What you can do, rather than minimizing the shrinkage, is you can manage the shrinkage. Rather than building a very long concrete road in one concrete pour, you break the road up into different sections, usually no more than about 4 or 5 meters in length, and you put a small 1 centimeter gap in between the concrete sections. Now that will mean that when it starts shrinking, the shrinkage is going to happen at those gaps, and so the concrete won't crack in the middle. Now you can see this all over the place. If you are walking to the white building in the at UKH, and you're walking there from the entranceway, you will notice that the footpath, every 2-3 meters, there's what's called a contraction joint, a small gap in the concrete that has been sliced through the concrete while it was still wet. Or if you go to Naz City or Shaka Zakaria, close to Bakhtiari, there's a concrete road going to the entranceway of that apartment block. And as you're driving your car along the concrete road, you're going to hear a kadunk, 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 probably every second as your tyres drive over a small contraction joint. So that's a way you can manage the shrinkage, and this seems to be one of the things which engineers often forget, or constructors often forget, and if there isn't an engineer overlooking their work, they will just make a very long concrete footpath, and then they are confused as to why there's lots of cracks forming in the concrete. It's because of shrinkage, and the way they could have managed that is every few meters, maybe anywhere between 3 to 5 meters of the road or footpath, they could have put in a contraction joint. That would have stopped the concrete from cracking. So we've talked a little bit about shrinkage now. I now want to talk to you about durability. Now I did mention that concrete improves with age. It actually gets stronger the older it is, like a fine wine. Well, like a fine wine, that is dependent on you looking after the concrete. If I had a bottle of wine and I opened it and I drank some of it and I said, that's a nice bit of wine, but I'm going to wait for it to get older so it gets better, and I just leave the bottle open sitting on the bench for many years, and then I come back to it, it's not going to be better. That wine is going to turn to vinegar. It's going to be revolting. Now, it's similar with concrete. Concrete will improve in strength with age so long as you look after it. Usually, though, concrete is exposed to the natural elements of wind and rain and hail and snow and acid rain. Because we're building civil engineering infrastructure, it's going to be exposed to natural elements and natural disasters, and that can break down the concrete in a form called weathering. Now, weathering is basically where large particles are broken down into smaller particles, and almost immediately after that happens you have erosion, where the concrete will erode. Now, so durability is basically a reference to a concrete's resistance to weathering. Now, with weathering, with concrete, there's really two ways that happens regularly in Kurdistan. Well, there's three ways. The first two are alkali-silica reactions, freeze-thaw cycles. Sulfate attack we're not going to be learning about because that's really only happening when you have very, very volcanic soils, and you don't have that with high sulfur content, and you just don't have that in Kurdistan. But there's another one there which isn't on the slide, and that's just from impact. If you build a concrete road barrier, if cars are going to be crashing and smashing into the concrete over time, that concrete is going to crack and get weaker. Now that one may seem obvious, but let's talk about alkali-silica reactions and freeze-thaw cycles and how they weather and break down the concrete, making the concrete weaker. Well, first off, let's talk about alkali-silica reactions. Now, even though cement is usually made up of calcium silicates and calcium aluminates, there's also a large number of alkali molecules inside the cement. Things such as salts, sodium chloride or disodium oxide, for example. And they're in there just as impurities in the cement. It's part of the process of making cement. There's always going to be a lot of these alkali salts or oxides inside the cement as well. Now, what can happen is over time that can react with silicas which are found in the aggregate. So all aggregates have some level of silica inside them. And this can cause all sorts of reactions which form crystallization. So here's an example of a reaction that takes place. You've got disodium oxide from the cement reacting with silica from the aggregate, and that forms sodium silicate crystals. Now this is just an example of a chemical reaction, but that can occur with alkali-silica reactions in the concrete. But there's hundreds of different reactions that can take place between alkali and silica. Now, what you need to know is that these take place over many years, so it happens only as the concrete is getting old, through many decades of age, but then civil engineering infrastructure needs to last a long time. We're not just interested in it standing up for 1 year or 2 years. We're interested in it standing up for a long period of time, many generations. But the important thing you need to know about alkali-silica reactions is that the product is a crystal. It actually expands and forms a matrix crystal. Now that's important for you to know, because that product, that crystal, is far bigger in volume than the reactants. And that's going to lead the aggregate particles, where the crystals are forming on the surface of the aggregate, they're going to bulk up, they're going to increase in volume, and that's going to lead to millions and millions of micro cracks beginning to form, initially too small for you to even see with the human eye. They're going to start happening throughout the concrete, and that's going to weather the concrete, erode it, and the concrete will get weaker. Now, just a little bit of trivia for you. I hope you all liked Breaking Bad, the TV show. I really enjoyed it. But you would have noticed that the crystals that they were making, the crystal meth they were making on that TV show, were blue in colour. That's absolute rubbish. Crystal meth is usually yellow in colour. I know that because I read about it online, not because of experience. But the blue colour of their crystal meth was basically because they were using sodium silicate crystals as a prop. Obviously, they weren't making crystal meth, they were just using sodium silicate crystals. And so you can imagine that sodium silicate crystals, these little blue crystals, if they started expanding and forming inside the concrete, they're going to push the cement and the aggregate apart, and there's going to be cracks forming throughout the concrete. So that's an alkali-silica reaction, and that's how it leads to weathering and a weakening of the concrete throughout time. So how do we avoid alkali-silica reactions? Well, we can avoid this by making sure that we actually have a cement that has very low alkali content, or an aggregate that has a very low silica content. Now, if you are using limestone or volcanic rocks as your aggregates, they tend to have very high silica content. So this is a problem in New Zealand where we have volcanic rocks, but also it's a big problem in places like Kurdistan where you're often using limestone or dolomite, a more compacted form of limestone, in your aggregate. So that silica will react with alkali in the cement. So if you've got concrete where you know there's a big issue of alkali-silica reactions bringing down the durability, you could use an aggregate that has a lower silica content, something like a river gravel or a granite. It would be more expensive, but that's one way you could avoid it. Another way is you could actually use a Portland blend cement which is mixed with fly ash or slag, and that basically means that the alkali in the Portland cement is basically deneutralized. The fly ash or slag basically acts as an inhibitor, and it stops the alkali from reacting with the silica, or it slows it down considerably. The other thing you can do is you can keep the concrete dry. One of the things that needs to occur that needs to be present for the alkali silica reaction to take place is water. That's why the alkali silica reaction always happens on the surface of the concrete initially, because that's exposed to water. So you need to find a way to keep the concrete dry. Well, that's easy if the concrete is indoors, but what if it's a concrete road barrier, or what if it's a roof? Well, one thing you could do is potentially you could paint the concrete. That might be too expensive and you have to maintain the paint, but that might be an option too. If you keep the concrete away from water, then that's going to stop alkali silica reactions. So you've got a few different ways of minimizing the alkali silica deterioration of the concrete, and the option you choose will depend on the cost and the application of the concrete. Now you can see in those two photos below, those are concrete road barriers, and they've got all these dark cracks forming on the surface of the concrete. That's an alkali silica reaction. Those concrete barriers are exposed to moisture a lot, where it's often raining, it's getting wet and dry a lot, and the alkali in the cement is slowly reacting through the years with silica in the aggregate. And so after maybe 3-4 years, you might start to see that you've got all these cracks forming on the face of the concrete barrier. So that's going to make the concrete barrier weaker. I now want to talk to you about freeze-thaw reactions. I don't know if you've realized, but water is the only molecule, it's the only substance that we have in the world, or in the universe in fact, that we know of, that when we freeze it, it goes from liquid to solid, and it actually expands. The volume increases. For most elements and for most molecules, when you freeze it, it will actually shrink. It will get smaller in volume. But for water, and I don't think anyone really fully knows why. I've read some articles on this, but it's all really theory-based. Water will actually expand. And you've probably done this. Have you ever bought a can of Coke and you've put it in the freezer, and you thought, I'll just freeze it for a little bit. I'm not going to freeze it solid. I just want to cool the Coke so I can drink it because the Coke is warm. And then basically the water in the Coke expands and the can explodes. And then your mum's really angry at you because you've got Coke all through the fridge. Well, that's one of the reasons why the new Coke or Pepsi cans are the shape they are. Next time you buy a Coke, or maybe when we get back to class, you could buy Mr. Allen a Coke and bring it to him in class and he can show you. But the bottom of the can is actually concave. It's actually got a little bubble into the can, and that creates room for, if it's frozen, that can pop out. And so it means that the can is ruined, but the Coke doesn't explode. Well, that's because water is freezing. Now, this is a problem for concrete. Remember how I said that concrete has a small amount of permeability. That means there's small channels going into the concrete. and that's basically from when water that was excess in the concrete mix evaporated, along with calcium hydroxides and other unwanted gases. And so if you look at concrete under a microscope, it's going to look a little bit like Swiss cheese. There's going to be lots of tiny little channels going into the concrete. And we want to minimize that if we want to build a strong concrete, because that just increases the void ratio. The more dense the concrete is, generally the stronger it is. Now, what happens if you have a concrete roof for a building in Shoresh, for example, and it rains and that roof gets wet and it forms a small puddle on the concrete roof? That water is going to go into those tiny little channels inside the concrete. And then at night, because it's winter and you're in Shoresh, that water, that puddle, it freezes. And the water in those tiny little micro cracks or channels, they expand, and it pushes the channel open a bit more. It cracks it open a tiny bit more. In the morning, the water thaws, it turns back to liquid, but at night it freezes again. And so it pushes the crack open a little bit more. And this can happen all through the winter. And all this time, it's causing little cracks, the cracks to get bigger. It thaws so the water can permeate deeper into the crack, and then it freezes, opening the crack a bit more. And this can happen again and again throughout the winter. It can also happen through seasonal cycles between summer and winter. But in places where there's a lot of hot and cold temperatures, where there's a lot of freezing and thawing, you have a problem with freeze-thaw cracks emerging in the concrete. Now that's Kurdistan. Kurdistan, it gets very hot in the summer, very cold in the winter. Often it's hot in the daytime and cold at night, and so water can freeze and it can thaw. It can go from liquid to solid and solid to liquid, and those cycles can be cracking the concrete. If this isn't clear to you, ask me during one of the tutorials, and I will try to show this to you on the whiteboard by drawing a diagram, okay? But this is what a freeze-thaw cycle will look like. You end up, similar to the alkali-silica reaction, you end up getting lots of cracks forming throughout the concrete, and usually they're a little bit more sparse and more evenly spaced than the alkali-silica reaction cracks, and usually they're a bit deeper, but that's going to weaken the concrete. So this seems to be a big issue for a lot of houses in Shoresh, but also in Slimani and even in Erbil. People will build a house here with a concrete roof, and then after a few years it starts to leak. Why is it suddenly starting to leak? Well, a lot of it probably has to do with freeze-thaw cracking, where there's freezing of water on the roof in the winter, and then it at night, and then in the morning it melts, and then it freezes again, and that leads to a series of cracks forming in the roof. So this is something that you need to consider, especially for things like roofs, where it's very important that the roof stays waterproof. But it's also important for all concrete where strength is an important factor, because obviously with all of these cracks, freeze-thaw cracking, alkali-silica cracking, they will deteriorate the strength of the concrete as it gets older. So how can we prevent freeze-thaw cracking? Well, We could just say, well, we don't build the house in Shoresh where there's a lot of freezing at night and cooling during the day, but that's probably not an option. We want to be able to build houses in Shoresh and Choman. We can't just have those people living in tents. But the easiest way is when you make your concrete, make sure you reduce the permeability. That means reduce the amount of channels where water and calcium hydroxide evaporate from the concrete. Now, how do we do that? Well, we can first off, we basically need to reduce the void ratio, the amount of air inside the concrete. Well, you can do that first by ensuring that you cure correctly. Curing is already important because that reduces the void ratio and that increases the strength of the concrete, but it also prevents, it gives it resistance to freeze-thaw. You can also use finer aggregates and cement. Now what that does is it means that the cement will have more reaction with water at a faster reaction rate and so forth. So that means you don't need to cure for as long. It also means that if the concrete is well graded and it has fine aggregate in that grading mix, then the areas which are solely cement and water, they're going to be much smaller. Those volumes are going to be smaller. And that means you're not going to have such large channels forming inside the concrete, which water can permeate. The other thing is that Portland cement does tend to have quite a high surface area. It means it does actually have quite a high number of water voids where the water was evaporating on the surface of the concrete. It may seem very smooth to the naked eye, but if you look at it under a microscope, you do have this Swiss cheese look to it, where you've got all these channels going into the concrete. So using a blended cement or lime, that reduces it. Both of those have a slower reaction rate, and they can actually mean, and that means that water sits there longer and it slowly reacts. And it basically, excess water evaporates faster because it's got a higher heat of hydration, and then the water that is needed for the cement reacts quickly. And then it closes over the channels because the excess water evaporates while the concrete is still liquid, still a sludge. And so all of those ways are ways you can reduce the permeability of the concrete, and that gives it resistance to freeze-thaw cracking. So unfortunately, Kurdistan has an issue with poor quality concrete, and what I'm talking about here is these these concrete blocks. What's the problem with these limestone concrete blocks? You see them everywhere, don't you? Well, they're used for building houses, for buildings. And have you noticed that houses, buildings in Kurdistan do not last a very long time? They might last for 20, 30 years max, but they don't last for hundreds of years. You can't sell the house to other people. The price of second-hand houses is very low in Erbil, and people tend to not inherit houses. Well, the problem with this is, first off, it's very high permeability. You can see that by just the high roughness on the surface of the brick, and it needs to have a certain amount of permeability so the bricks will stick together. We'll talk more about that when we do masonry. But the main reason is basically they haven't used enough fine aggregate. They and Fine aggregate is more expensive, so it's all down to economy. It's also very poorly graded, and that leads to a rough surface and high permeability. It's also often exposed to moisture. These blocks are used for walls where it rains on them. And even if you do paint it, often the paint is not maintained, and so water gets in behind the paint. It uses a limestone aggregate. So one of those things is the limestone aggregate has a very high porosity. So those aggregates can get water into the aggregate particle itself and expand the aggregate particle. That breaks down the concrete. It also has quite a high alkali content, a very high silica content in the limestone. So with the high alkali content, with the cheaper cement they're using, there can be alkali silica reactions. High surface area, that's related to the high permeability. And finally, they often don't cure them for very long. They might cure them for maybe a day or two, and often all they're doing is sprinkling it with water. So even in that 2-3 days of curing, it's often drying in that time anyway. So very poor quality management. Now, all of these things are basically down to economy. People trying to make a material which is cheap, but it leads to piss poor performance. These concrete blocks, they do not last very long. They crack with freeze-thaw cracks, alkali silica cracks, porosity in the aggregate cracks, and they break down in time. So these are two photos that were taken just outside Mosul. And it was kind of interesting. These photos were taken by Al Jazeera, the news agency, and they were talking about the decay of war, how buildings were basically being bombed and destroyed. The funny thing is that both of these photos, they were not destroyed by war. They were destroyed by the elements. They were destroyed by water and the general erosion of the concrete blocks inside. So that these buildings are no older than maybe 20-30 years old, and you can see that they haven't been maintained, and they don't just stay as they are, they've actually decayed considerably. So Kurdistan is not the only place where this is an issue. You have this old house. This is from England, and you can also see on the inside there's actually cracks forming between the blocks because also the mortar is decaying. Now, this house was built illegally. Now, in the UK and New Zealand and Australia and America and much of Europe and much of Asia as well, places where it's the developed world rather than the developing world, you have to realize that you're not allowed to build a house out of concrete blocks of that quality. Concrete breeze blocks, we call them, are not suitable because of the low durability and also very poor insulation. Now that's why we can use these blocks for building barns for animals to live in, but we can't use them for residential houses. So isn't that a little bit depressing that the way we're building houses in Kurdistan, that is not fit according to the building standards for much of the developed world. It's only suitable for animals to live in. That's a little bit depressing, and that's because of the low durability and also the low insulation. And here's an example of low durability. Again, this is a photo in Tikrit, and you can see that in the bottom right hand corner, this is on the outskirts of Tikrit in Iraq, and you can see that they've built a small building there using concrete breeze blocks. And basically, over time, probably more with alkali silica reactions and with porosity in the limestone rather than limestone aggregate rather than freeze thaw reactions because it's secrete, you can see that the blocks have actually decayed in time and they've broken down and turned to rubble and sand. And the real crazy thing is if you look closely at that wall, you can see that the mortar, the cement that holds those blocks together, that is stronger than the block. The mortar is still standing. That is incredible because usually the mortar is the weakest part of the concrete wall and the less durable. Now that is not an old ruin from ancient Sumeria. That was built only 20 years ago. And you can see how quickly it decayed. Now compare that with the library in Ephesus. That's built from limestone marble, and it's not made from a concrete, but you can see how well that's been maintained. In 2,000 years, the facade of that library hasn't fallen down. The rest of the library actually was destroyed in war. People had to break it down, but the facade remained. So that gives you an example of just how temporary people's thinking is today with building certain civil engineering infrastructure. And they build it with materials with very low durability. Now, I want to just say that I hope that I'm not too negative about Iraq or Kurdistan with my last slides there. I think it's a fantastic country I get to live in and work in, but and there's a lot of reasons for the very temporary mindset with building civil engineering infrastructure in this country. We'll talk more about that when we get to engineering economics. But generally, there is a lot of room for improvement in Kurdistan to use better materials than concrete breeze blocks. That will have better durability and will be beneficial not just for the immediate owner but future generations. That's all I've got to share with you on concrete in the building materials class. If you want to do any supplementary reading, then go to the Civil Engineering Materials book. Again, this is available in the library should we get back, but if you want it, just to answer a query I got from Mubin today, it's not available as a PDF online. What you need to do is you can buy the book as a Kindle file. So this is by ordering it through Amazon, and then in order to read it, if you don't have a Kindle tablet, you need to download the Kindle app onto your laptop or phone, and then you can read it. This is not required reading, it's not compulsory reading, this is just supplementary recommended reading, and I recommend you do this, especially if you prefer to learn by reading English rather than listening to English. If you are falling asleep during these lectures, well, first off, you should be pausing the lectures and refreshing yourself and coming back to listen to some more. But you could, in fact, read all of the material in these books, in this book, the Civil Engineering Materials. It's supplementary reading. Remember everything that you need. One moment. Yeah, sorry about that. What I was saying was that with this supplementary reading, all the material that you need for the exams and the assignments, I'm teaching that to you in the lecture. There's no additional learning to be made from the book. It's going over the same material. So just keep that in mind. Okay, thank you and God bless. Bye.